Gaussian or normal, what we call normal distribution, right? Normal. We talk about normal in our day-to-day language. That normal comes from this Gaussian, invented by the mathematician Gauss. Okay. So we have told this is the normal distribution. This is most important and most widely used. Okay. And what are the properties of this? So let me give you the graph. I have discussed about this in the last video also, and we know about this bell-shaped curve, and we discuss about it all the time. So it is most widely studied, most widely used. So this is the thing that you see all the time. This is the shape. This is equal to mu equal to mean. Okay. So if you see here, the density and this axis, okay, say for example, if we give, say, this axis is there, and this gives us the probability. Okay, this probability here. If you say here, around the mean, the probability of finding something is highest. This is the axis around which we'll get the probability. So around the mean, the probability is highest. And as you go away from the mean, the probability decreases. So this is what density means. The distribution is most dense around the mean here in this distribution. Here in uniform, you saw, right, it was constant everywhere. The mean will be somewhere in the middle, but it is constant, it doesn't change. Okay, even it's symmetrical around the mean, but it is uniform, there's no change. But here, if you see, the density is maximum, the probability of finding something is maximum around the mean, and as we move away from the mean, the density keeps on increasing on the either side, and it is also symmetrical. Okay, and this is what is our sigma. This is our standard deviation, this distance here. And the more wide, if it is like very close, so if it can be very thin also. So then we know that the spread is very here, if you see, the sigma is less, the spread is less, the standard deviation is less, everything is very close to mean. So as it spreads out, the spread of the data or the variance of the data is very large. Means we have a lot of variety or a lot of information or a lot of variability in the data. And if it is thin, means everything is around the mean only and there's not much change. Here, if you see, that is the spread is large, means there's more variability in the data. That is, more different types of data is present. And as you go, like, it will become more wider and more taper, right? So means there is more variability in the data. This is what it means. So this means that data is, okay, this is clustered symmetrically around mean. Okay, and around the central average. Okay, and as we move away from the center, the value keeps on decreasing. So the most frequent, most outcomes are average and extremely high or extremely low value. As you go, this will go to 0. As you go to minus infinity, this will become 0. As you go to plus infinity, this will become 0. So extremely high or extremely low values are very rare. This is what it says. Okay, and extreme values, extremely low or high values are rare. For example, as I mentioned earlier, that if we use this heights of people, Indian people, so if the average height is say 165 centimeter, then probability of finding someone of 100 centimeter is very low. Similarly, probability of finding someone of 200 centimeter is very low, but there will be someone of that height. But as we go away from it, it will be very low. But the maximum probability of finding someone, would be around this 165 centimeter mark. This is our average height. This is what it means. Okay. And the most important thing is, if we have a sample data, okay, so we know that we are sampling we have samples of heights of people of India. If we have the data, then we can easily calculate its mu, mean, and standard deviation, sigma given by, this is sigma given by standard deviation, and that variance is sigma square. Sigma square is equal to variance, that is your spread or variability. Okay, so as soon as we have our data, we can calculate this. And now once we know this, we have a lot of beautiful things. So we have the formula, the probability distribution function of a Gaussian is given by the PDF is given by, okay, so this is given by, so generally the notation, okay, so let me write the PDF first. PDF is given by f of x is equal to 1 by sigma into root 2 pi, this is e to the power minus of x to the power mu whole square by 2 sigma square. So this has been, okay, this has been derived, and there are a lot of beautiful properties of this. The most beautiful application of Gaussian we use is central limit theorem, which we'll discuss about later in one of the videos. Okay, anything can be modified and molded to fit into this Gaussian using the central limit theorem. Okay, it's very beautiful property, and that's what gives it so much power. So you see, once I know the mu, okay, and the sigma, from that I can formulate the probability of any point on this hole, and a lot of other beautiful properties around this. Okay, that's the power of this, and any data can be converted. So there's one thing called standardization that we'll discuss again. So any data can be standardized. Standardized means mean centered. So like it can be said z is equal to x minus mu by sigma, that is mean centered, and this is 1 by sigma, so this is called and mean centered plus variance scaled. So this is standardization. There's one normal distribution, very common, that is standard normal distribution, what we call is, okay, a commonly used term that is used widely when we standardize it. So there's something called standard normal distribution when the mean is 0 and the variance is 1. So this is given by x belongs to n 0 comma 1. So when we have such a equation, we call that this is standard, and in general it is whatever it is given by, it is given by normal, that is n and g are used, it is given by mu and sigma square. This is our variance, this is our mean, so I'll write it down. If we know the mean and the variance, that information is sufficient, and then we get a lot of information about, beautiful information about Gaussian, most studied and everything. So many a times in machine learning, everywhere you will see that most of the things are modeled around. So if I give you the example already, right? For example, height of people is Gaussian. Okay, their IQ scores are Gaussian. Errors in scientific experiments are Gaussian. This is the basis. Okay, this is the basis for linear regression also. This is the one of the most basic assumptions in linear regression, that errors are Gaussian distributed, and this gives the rest of the maths follows after that. I hope Gaussian is clear. Okay, so there's one more very beautiful rule. Okay, so let me talk about that. So you must have heard about, there is something called 68, 95, 99 rule around for Gaussian. Okay, so what does it mean, 68, 95, 99 rule? This means that 68% of data approximately, it is approximate values, this is 68.2, this is 95.4, and this is 99.7. so we'll talk about approximately. 68% of data lies or falls within one standard deviation. Standard deviation, everything, if you don't know, when we study statistics again, I'll revise these concepts for you, and I'll put the link of those videos in the description. So this is equal to mu plus minus sigma. Okay, so that is 1. then 95% of data falls within 2 standard deviation, that is mu plus minus 2 sigma, and 99% of data falls within 3 standard deviation, that is mu plus minus 3 sigma. Okay, so if you see from this graph, right, so plus minus means plus sigma this side, minus sigma this side. So if I go plus sigma here, plus sigma this side, minus sigma, so within this region my 68% of data will be there. 2 standard deviation here, so 95% data will be here. If I go 3 standard deviation like this, so till here 99% of the data will be here. So this is so much studied that we know this is very commonly used everywhere. Okay, and all these numbers we remember from this PDF and CDF, right? What is the CDF? If we have the PDF, how do we find the CDF? Cumulative distribution function. So CDF is nothing but integral of PDF, right? Fx dx. So if we know the Gaussian distribution, what is the Gaussian distribution PDF? The PDF is given by 1 by sigma root 2 pi exponential, I'll write it like this, minus of x minus mu whole square by 2 sigma square dx. Okay, so the 68% data, okay, will be falling within, if we integrate it from minus sigma to plus sigma. Okay, 95% of data will fall from similarly minus 2 sigma to plus 2 sigma, and rest of the things. And similarly 99% of the data. Okay, you can figure that out. So that's why integration is important to understand this. So if you want for some fun practice, you can try integrating this and find out that if you integrate this from this range to this range, this will give you this values. This will be around 68.2, this will be 95.4, and this will be 99.7 for the 3 standard deviation. Okay, check that out. That will be a fun exercise. Okay, with this Gaussian is done.